Good evening, welcome back, or if this is your first time here, welcome. Tonight we're going to explore something vast and ancient, something you've seen countless times but perhaps never fully considered. We'll discover the Milky Way, our home galaxy, slowly and patiently, moving through thousands of years of human observation, from ancient people staring up at a mysterious band of light across the sky, through the patient work of astronomers mapping what we're inside of, to understanding our place in a vast spiral of hundreds of billions of stars. We'll begin with ancient observers trying to make sense of a pale glow stretching across the darkness, stand beside Galileo as he first resolves it into individual stars through his primitive telescope. Watch William Herschel spend decades counting stars to map the shape of our cosmic home, and follow the discoveries that revealed we're not alone, that our galaxy is just one island universe among billions in an expanding cosmos. If this story helps you rest tonight, feel free to like or subscribe, though there's no pressure. I'm always curious where you're listening from, so if you feel like it, comment your city and what time it is there. Perhaps you're under dark skies where the Milky Way is visible, or perhaps you're in a city where light pollution has hidden it, making you forget it's always there above you, streaming across the heavens as it has for billions of years. Dim the lights now, if you haven't already. Adjust your pillow, finding that comfortable position. Maybe turn on a fan for some gentle white noise, or simply let the quiet settle around you like the darkness between stars. We have thousands of years of cosmic discovery ahead of us, but we'll take it slowly, one observation at a time, one realization after another, the patient accumulation of understanding that characterizes astronomy, the slowest of sciences. Let's begin. Imagine you are standing on a hillside in ancient Greece, perhaps near Athens, on a warm summer night around 400 BCE. The air is cooling after the heat of the day, carrying the scent of dry grass and Mediterranean herbs, oregano and thyme releasing their fragrance as evening breezes move across the slope. The city below shows scattered lights, olive oil lamps flickering in windows, far fewer than modern cities, nothing that could truly compete with the darkness above. You're a philosopher, perhaps a student at Plato's Academy, and you've walked outside the city walls specifically to observe the heavens, to contemplate the cosmos as your teachers have instructed. Philosophy in this era means natural philosophy, attempting to understand the physical world through observation and reason, the sky being one of the great mysteries demanding explanation. The night is clear, the kind of crystalline darkness that's become rare in the modern world. No moon tonight, the stars emerging as the last glow of sunset fades from the western horizon. Your eyes adjust slowly to the darkness, a process taking perhaps 20 minutes, your pupils dilating, the sensitivity of your vision increasing, revealing more and more stars as the minutes pass. First, the brightest stars appear, Vega and Arcturus and Altair, the familiar bright points that ancient navigators know by name. Then fainter stars emerge, filling in the constellations, Hercules and Ophiuchus and Scorpius, the patterns that humans have traced across the sky for generations. And finally, as your eyes reach their maximum sensitivity, you notice something else, something more subtle and mysterious. A pale band of light stretches across the sky from horizon to horizon, a cloudy glow that doesn't fit with the point-like nature of stars, something milky and diffuse, slightly brighter in some regions and fainter in others, broken by dark patches that seem to be gaps or rifts in the glow. The band arches overhead, passing through certain constellations, its path fixed among the stars, not moving like the moon or planets, but remaining stationary against the celestial sphere, part of the fixed heavens that rotate together through the night. This is what the Greeks call the galaxias kyklos, the Milky Circle, though you know it by various names and stories. One myth says it's milk spilled from the breast of the goddess Hera, the queen of the gods, Zeus having tried to trick her into nursing the infant Heracles to grant him immortality, the goddess pulling away and her milk spraying across the heavens. Though ancient observers thought the Milky Way was milk spilled across the sky, a poetic explanation modern astrophysics would find charming but inaccurate. Another story describes it as a seam where the two halves of the celestial sphere were joined in creation, a cosmic construction detail visible if you know where to look. But you're attempting natural philosophy, not mythology, trying to understand what this band actually is through reason and observation. Democritus, whose writings you've studied, proposed it might be the light of many small stars packed too closely together to distinguish individually, their combined glow creating the milky appearance. It's a remarkably prescient guess, though without instruments to verify it, it remains speculation among many competing theories. Aristotle argues differently, suggesting it's an ignition of the dry, fiery exhalation of the Earth in the upper atmosphere, connecting it to other atmospheric phenomena like comets. The debate continues, natural philosophers discussing the nature of the heavens in the Academy's gardens during the day, testing their theories against observations each night. The weight of not knowing presses on you as you lie back on the hillside, grass beneath you, the vast sky above, the milky band stretching in both directions, disappearing below both horizons. The mystery is profound, the sense that you're looking at something significant but lacking the tools or knowledge to understand it, that future generations might solve what remains opaque to you. The cool air grows cooler as night deepens, dew beginning to form on the grass, dampness seeping through your cloak, but still you watch, trying to commit the details to memory, the exact path of the glow, the stars it passes through, the variations in its brightness. Time passes, centuries accumulate. You now find yourself in Babylon, that ancient city in Mesopotamia, the cradle of systematic astronomy. It's perhaps 300 BCE, the city under Seleucid rule after Alexander's conquests, but the astronomical traditions stretching back 1,000 years, the priesthood maintaining continuous records of celestial phenomena, the patient accumulation of observations across generations. Imagine you're an astronomer priest, trained in the cuneiform writing system, responsible for recording celestial events and calculating astronomical tables. The ziggurat rises above the city, its massive stepped structure providing an elevated platform for observations away from the dust and heat of ground level, closer to the heavens both literally and symbolically. You climb the stairs in the evening, carrying clay tablets and a stylus, your tools for recording the night's observations. The ritual of ascending is familiar, the count of steps memorized, your breathing steady despite the climb, the smell of the city fading as you rise, replaced by cleaner air moving across the elevated platform. The top of the ziggurat is flat, paved with fired brick, providing a stable observing platform. The horizon is visible in all directions, nothing obstructing your view except the buildings of Babylon below, spreading in all directions, the Euphrates River visible as a dark band reflecting starlight. The Milky Band stretches across the sky here too, following the same path relative to the stars as it did in Greece, though the specific constellations have different names in Babylonian tradition, different stories attached to the same patterns. Your astronomical work focuses primarily on the planets and the moon, tracking their positions against the background stars, recording eclipses and conjunctions, calculating cycles and periodicities that allow prediction of future events. The Babylonian mathematical astronomy is sophisticated, using numerical tables to predict lunar positions accurate enough for practical purposes, though the physical nature of the heavens remains mysterious. The Milky Band is noted but not central to your calculations, a permanent feature of the sky, unchanging, not one of the wandering objects that demand careful tracking. But you do record it, noting which zodiacal constellations it passes through, describing its appearance in careful cuneiform marks pressed into soft clay with your stylus. The tablets fired and stored in the temple libraries, joining thousands of others, the accumulated observations of centuries. The scratch of stylus on clay is rhythmic, methodical, the sound of knowledge being preserved, the patient work of recording that characterizes Babylonian astronomy. The night is warm, the air still, occasionally carrying the smell of smoke from the city below, the murmur of the nighttime city faint at this height. The stars rotate through the night, Sirius rising in the east, the familiar rhythm of the celestial sphere's rotation, 1 degree every 4 minutes, completing a full circle in approximately 24 hours. The Milky Band participates in this rotation, fixed to the celestial sphere, always maintaining the same relationship with the stars, another piece of evidence that it's part of the heavens rather than an atmospheric phenomenon that might shift or change position. Centuries continue to pass. You now find yourself in China, perhaps during the Han Dynasty, around 100 BCE. Chinese astronomy has its own ancient traditions, court astrologers maintaining careful records, celestial phenomena being interpreted as omens affecting the emperor and the state, the importance of astronomical observation being both practical and political. Imagine you're a court astrologer, responsible for interpreting celestial signs, reporting unusual phenomena to the emperor, maintaining the calendar, and predicting eclipses. The observing platform is in the palace complex, a raised wooden structure designed for sky watching, equipped with various instruments for measuring positions and angles, armillary spheres and sighting tubes, bronze and wood construction, the metal cool to the touch in the evening air. You've studied the classic texts, mastered the constellations of the Chinese system, very different from Greek or Babylonian patterns, dividing the sky into 28 mansions corresponding to the moon's monthly cycle, organizing the heavens according to Chinese cosmological principles. The Milky Way you call the Tianhe, the celestial river or silver river, imagining it as a great waterway in the heavens, separating the Weaver Girl star from the Cowherd star. The tragic lovers allowed to meet only once per year when magpies form a bridge across the river, the Chixi festival celebrating this annual reunion. The mythology is different from Greek stories, but serves the same purpose, making sense of the mysterious, luminous band through narrative, connecting it to human concerns and seasonal cycles. Your observations are recorded in careful characters brushed onto silk or bamboo strips, organized according to systematic categories, unusual phenomena separated from regular occurrences, comets and supernovae, and meteors all carefully described, providing future historians with valuable records of transient events. The celestial river is permanent, always present, its path noted but not requiring the urgent attention given to omens like comets or planetary conjunctions. But you record its appearance regularly, noting when it's highest in the sky, when certain constellations pass through it, the patient documentation that characterizes Chinese astronomical tradition. The smell of ink and paper is familiar, your workspace illuminated by oil lamps with red paper shades, red light preserving your night vision better than white light, a practical knowledge gained through centuries of astronomical work. The sounds of the night garden surround you, insects chirping, occasionally a nightbird calling, the rustle of bamboo in the breeze, the isolated quiet of nighttime observation work, removed from the daytime bustle of the palace, the contemplative solitude of watching the sky. Time flows forward. You find yourself among nomadic peoples crossing vast deserts, perhaps the Bedouin of Arabia or the indigenous peoples of Australia, cultures where navigation by stars is essential knowledge, where the sky is read like a map, where intimate familiarity with celestial patterns means survival. The Milky Way serves as a navigation aid, its path marking directions, its seasonal changes indicating the passage of time, its presence reliable where few other landmarks exist in the endless sameness of desert or outback. Aboriginal Australians see the dark patches in the Milky Way as significant, the rifts and gaps where the glow is blocked by dust clouds, perceiving these dark nebulae as the emu in the sky, a cosmic bird whose shape is defined by absence rather than light, a different way of pattern making than connecting bright stars. The stories explain the seasons, the emu visible in autumn when actual emus are laying eggs, the sky story connecting to earthly cycles, knowledge encoded in mythology, transmitted orally across generations. The desert night is cold, temperatures dropping sharply after sunset, the air extremely dry, the sky darker than in humid climates, the transparency perfect, stars visible down to the horizon in all directions, no trees or buildings to obstruct the view, nothing but endless sky above and endless earth below. You lie on the sand, warmth still radiating from beneath you though the surface is cooling, and watch the Milky Way arc overhead, so bright under these perfect conditions that it actually casts faint shadows, the combined light of billions of stars becoming tangible, visible influence on the earthly world. The experience is profound, the connection to the cosmos direct and immediate, no theory or instruments mediating the observation, just human eyes and the ancient light reaching them. The same photons that travelled for hundreds or thousands of years now entering your pupils, triggering chemical reactions in your retinas, creating the sensation of vision, the awareness of the vastness above. The question of what the Milky Way actually is remains mysterious, but its presence is undeniable, its beauty obvious, its utility as a navigational reference practical. Remember these ancient observers, all of them seeing the same phenomenon, all of them wondering, all of them creating stories to explain the mystery. The Greeks and Babylonians and Chinese and Bedouin and Aboriginal peoples, separated by distance and culture, all looking up at the same galactic plane from inside it, all attempting to make sense of what they saw with the knowledge available to them, the universal human impulse to understand the cosmos that contains us. Now imagine you stand in Padua, Italy, in the year 1609, a turning point in human understanding of the heavens. Galileo Galilei, professor of mathematics at the University of Padua, has recently learned of a device invented in the Netherlands, a tube with lenses that makes distant objects appear closer. Though originally intended for terrestrial use, for naval observers to spot distant ships, Galileo immediately recognized its potential for astronomy, for turning this spyglass toward the heavens to see what might be revealed. You find yourself in Galileo's workshop, the smell of brass filings and optical grinding compounds filling the air, workbenches cluttered with lenses and tubes, and partially assembled telescopes. The patient technical work of improving the design, increasing magnification while maintaining clarity, grinding and polishing lenses by hand, testing combinations, gradually improving the device until it magnifies 20 or 30 times, far better than the original Dutch toys. The first telescopic observations of the moon revealed mountains and craters, surface features that suggested the heavens aren't perfect unchanging spheres as Aristotelian philosophy maintained, but rather real places with geography, landscapes, terrain. The discovery of 4 moons orbiting Jupiter provided evidence for the Copernican system, showing that not everything orbits Earth, that multiple centres of motion exist. But when Galileo turned his telescope toward the Milky Way, the discovery was perhaps even more revolutionary, though less immediately controversial. Imagine you're with Galileo on a clear autumn night, November 1609, the telescope mounted on a simple wooden stand pointing toward the Milky Way where it passes through the constellation Sagittarius. The brass telescope tube is cold to the touch, the Venetian night air carrying moisture from the lagoon, dew forming on metal surfaces, requiring periodic wiping of the objective lens to maintain clarity. The telescope is small by later standards, perhaps 3 feet long, narrow, primitive, but revolutionary compared to naked eye observation. Galileo places his eye to the eyepiece, a small lens held in a brass fitting, and adjusts the focus by sliding the eyepiece tube in and out, the mechanism simple but effective. The field of view is tiny, just a fraction of a degree, seeing only a small portion of the sky at once, requiring careful aiming and scanning to build up an understanding of the larger region. The milky glow that appears as a diffuse cloud to the naked eye suddenly resolves. Individual stars appearing in the field of view, dozens of them, hundreds of them, too many to count, each one a point of light where before there was only a vague luminosity. The realization forms slowly as Galileo scans across the Milky Way, the pattern emerging, the understanding dawning. The milky appearance is created by countless stars, each too faint to see individually without optical aid, but collectively producing the glow visible to unaided eyes. Democritus was right, the ancient Greek philosopher who guessed it might be many small stars, his speculation confirmed by this simple telescope 2,000 years later. The validation of ancient insight through modern technology, the connection across centuries, the continuing human project of understanding. Galileo sketches what he sees by candlelight, drawing clusters of dots representing stars, attempting to capture the crowded fields, the rich star fields visible in the telescope, page after page of sketches showing different regions of the Milky Way. The patient documentation that allows him to later describe his discoveries in the Sidereus Nuncius, the Starry Messenger, the book published in 1610 that announced these telescopic discoveries to the learned world. The scratch of pen on paper, the smell of ink, the fatigue of keeping one eye closed for hours while observing, the cold numbness in fingers from handling brass and working in nighttime temperatures, the intellectual excitement of discovery competing with physical discomfort, the reality of astronomical work being less romantic than imagined, but more rewarding. Each star resolved is a small victory. Each cluster revealed adds to understanding, the slow accumulation of knowledge progressing point by point, observation by observation. But resolving the Milky Way into stars actually deepened certain mysteries rather than solving everything. If it's stars, why are they concentrated in this particular band across the sky? Why does the Milky Way have structure, bright regions and dark lanes, and variations in width and intensity? What determines the shape and extent of this system of stars? Are we inside something larger? The questions multiplied even as one question was answered, the pattern of scientific progress being that each answer generates new questions, deeper mysteries revealed by solving surface puzzles. The wider astronomical community learned of Galileo's discoveries as copies of Sidereus Nuncius spread across Europe, letters travelling by postal systems that took weeks or months to deliver messages between cities, astronomers corresponding, debating, attempting to replicate observations with their own telescopes, some confirming Galileo's claims, others struggling with poor instruments or unclear observations. The slow social process of scientific validation proceeding at the pace of early modern communication. Decades passed, telescopes improved, more astronomers observed the Milky Way telescopically, all confirming the basic discovery. Its stars, countless stars, too numerous and faint to see individually without optical aid. But the deeper questions remained unanswered through the 1600s and into the 1700s, the nature and structure of the system containing these stars being unclear, the puzzle of why they're arranged this way remaining unsolved. Time moves forward. You now find yourself in England in the late 1700s, an era of systematic survey astronomy, of patient cataloguing and mapping, of attempting to understand the larger structure through careful observation and statistical analysis. William Herschel, a musician turned astronomer, living in Bath and later Slough, has become obsessed with understanding the structure of what he calls the sidereal system, the system of stars comprising the visible universe. Herschel's approach is methodical, almost industrial in its systematic nature. He conducts stargaging, a technique he devised. Point the telescope at a particular region of sky, count all the stars visible in the field of view, record the number, move to an adjacent region, repeat. Do this for hundreds and thousands of different directions, building up a map of star density in different directions, using the assumption that more stars in a direction means the system of stars extends further in that direction, that by mapping the star density you can map the shape of the system containing them. Imagine you're Caroline Herschel, William's younger sister and scientific collaborator, on a cold English night in 1785. The Herschel telescope is enormous by the standards of the time, 20 feet long, mounted in a wooden framework in the garden, requiring coordinated effort to operate and aim. The night is clear but cold, your breath visible in the lantern light, frost forming on grass and metal surfaces, the observing work requiring physical endurance as well as intellectual dedication. William is at the eyepiece, peering through the telescope, calling out star counts as he sweeps the instrument across predetermined sections of sky. Your job is recording the observations, writing in ledgers by the faint red light of a shielded lantern, recording the direction, the time, the number of stars counted, maintaining the careful documentation that makes the survey scientifically valuable. The scratch of pen on paper is rhythmic, punctuated by William's voice calling out numbers 14, 21, 38. The variations in star density in different regions becoming apparent through accumulating data. The work is tedious, repetitive, demanding concentration hour after hour, night after night, month after month. One night's work might produce 50 or 100 star counts in different directions, each contributing one small data point to the larger survey. Weeks of clear nights accumulate into hundreds of observations, months into thousands, years into the comprehensive survey needed to map the sidereal system's shape. The patience required is extraordinary, the dedication absolute, the progress slow but steady. The smell of the night surrounds you, damp grass, and the metallic scent of telescope brass, occasionally smoke from a distant chimney carrying on the wind. The sounds are of the telescope mechanism, wooden framework creaking as the instrument moves, pulleys and ropes adjusting the aim, William's muffled voice from behind the telescope, your own breathing and the scratch of the pen, isolated sounds in the nighttime quiet of a provincial English town. The analysis of the accumulated data takes months of additional work, William drawing charts and diagrams, attempting to visualize what the star counts reveal about the system's shape. The conclusion he reaches is revolutionary. The system of stars is not spherical, but rather disc-shaped, flattened like a grindstone or a plate, much wider than it is thick, explaining why we see a band across the sky rather than an even glow in all directions. When we look along the plane of this disk, we see through a long path containing many stars, creating the milky glow. When we look perpendicular to the plane, through the thin direction, we see fewer stars, the darker regions between the Milky Band, the systematic difference in star density revealing the flattened geometry. Herschel further concluded that the Sun is located roughly near the centre of this disk, the system extending similar distances in all directions along the plane, his stargazing suggesting a relatively symmetric distribution with us near the middle. This conclusion was wrong, a limitation of his method, but the basic insight about disk shape was correct, a genuine advance in understanding structure. Scholars still debate exactly when Herschel realized the sidereal system was disc-shaped, and when he abandoned earlier ideas about it being more irregularly shaped, the development of his thinking proceeding through multiple papers over years, the evolution of scientific ideas being gradual rather than sudden revelation, understanding developing incrementally through accumulated evidence and reflection. Quirky detail. While conducting his sky surveys, Herschel discovered Uranus in 1781, the first planet found in historical times, initially thinking it was a comet before recognizing its planetary nature, the discovery making him famous and securing royal patronage that allowed him to build even larger telescopes. The 40-foot telescope at Slough, becoming the largest in the world for decades. Astronomical research being expensive and requiring wealthy patrons in this era before government funding. The years of stargazing produced understanding, but also revealed limitations. Herschel couldn't see the entire disk he hypothesized, couldn't directly confirm that the system had the shape his star count suggested, was inferring three-dimensional structure from two-dimensional observations. The fundamental difficulty of understanding the forest when you're standing inside it, trying to map a structure you're embedded within, lacking the external perspective that would make the task simple. The 19th century saw continued improvement in telescopes, better lenses and mirrors, larger apertures collecting more light and revealing fainter objects, steadier mountings allowing higher magnifications, gradual technical progress making observations more precise and reliable. But the fundamental limitation remained. Optical telescopes could only see through dust clouds a few thousand light years at most, the interstellar dust absorbing and scattering light, creating an effective horizon beyond which direct observation was impossible, the majority of the sidereal system hidden behind veils of dust. Time passes. You now find yourself in the era of photographic astronomy, the late 1800s and early 1900s, when glass plates coated with light-sensitive emulsions began replacing the human eye as the detector at the telescope, revolutionizing astronomy by allowing permanent records and revealing objects too faint for visual observation through accumulating light during long exposures. Imagine you're an astronomer at a major observatory, perhaps Lick Observatory in California or Mount Wilson, working with the large refractors and reflectors being built on mountaintops for optimal atmospheric conditions. The photographic process has its own rhythm and requirements. Glass plates must be prepared, coated with emulsion in the darkroom, loaded into plate holders, installed in the telescope, the exposure begun and timed precisely, the telescope guided manually to compensate for Earth's rotation during exposures lasting hours, the concentration required to keep a star perfectly centered on crosshairs through the eyepiece. Tiny adjustments every few seconds, the physical and mental endurance needed for successful photography. The observing begins at twilight, preparations made while light remains, the telescope pointed toward the target region before darkness is complete. The dome rumbles as it rotates, aligning its opening with the telescope's direction, cool night air flowing in as the shutters open. the transition from enclosed space to connection with the sky above, the smell of the mountain night, pine trees and thin air, the observatory located at high elevation for clearer skies, less atmospheric turbulence, better seeing conditions. The photographic plate is loaded, the exposure begins, the clock started, your eye at the guide eyepiece, watching a bright star, making tiny corrections to the telescope's motion, keeping the star centered hour after hour of concentrated effort. Your back aching from the posture, eyes straining in the red-lit dome. Patience required as photons accumulate on the emulsion, gradually building up an image too faint for eyes to perceive, but recorded by the chemical sensitivity of the photographic process. Dawn approaches, the eastern sky beginning to brighten. The exposure ended before twilight brightens the sky too much, the plate holder removed, carried to the darkroom for development. The nervous moment of developing, revealing whether the night's work was successful or wasted by clouds or guiding errors or technical problems, the image slowly appearing in the developing tray, dark sky, bright stars, the Milky Way appearing as a complex region of bright and dark areas, far more structure visible than the eye could perceive, the photographic plate revealing the detailed structure of the galaxy, dark dust lanes silhouetted against brighter star clouds, the architecture of our cosmic home rendered visible. The smell of the darkroom is distinctive, chemical developing solutions, fixer, the red safe light glow, the careful work of processing plates without exposing them to white light until fixed. The ritual of development as important as the observation itself, the plate becoming the permanent record, the scientific data that can be analysed at leisure, measured and studied without time pressure, multiple astronomers examining the same plate, comparing different plates of the same region taken at different times to detect changes or motion. The photographic surveys revealed that the Milky Way is complex, not a simple uniform band but full of structure, variations in brightness, dark rifts where dust blocks the light of stars behind, bright regions of intense star density, the detailed geography of the galaxy becoming visible for the first time, though the three-dimensional structure still required interpretation and inference. The surveys also revealed thousands of fuzzy patches, nebulous objects, scattered across the sky, some within the Milky Way band, others outside it, distributed across all regions. Some nebulae clearly resolved into stars when photographed with large telescopes, star clusters so distant their members appeared blended together visually. But others, particularly the spiral nebulae, remained mysterious, their nature debated, their distances uncertain, their relationship to the Milky Way system unclear. Remember Galileo resolving the Milky Way into stars? Now photographic plates revealed millions of those stars simultaneously, capturing regions far larger than any telescope's visual field of view. The power of photography to record faint details invisible to eyes. The technology enabling new scales of survey astronomy. This leads to the great debate of 1920, one of the most famous events in astronomical history, when Harlow Shapley and Heber Curtis met at the Smithsonian Museum of Natural History to debate the scale of the universe and the nature of spiral nebulae, their disagreement representing fundamental uncertainty about cosmic distances and structure. Imagine you're in the audience at this debate, April 26, 1920, listening to two prominent astronomers present competing visions of the cosmos. Shapley argued that the Milky Way system is enormous, hundreds of thousands of light years across, that globular clusters distributed around it mark out this vast scale, and that spiral nebulae are relatively nearby objects within this giant Milky Way system, not separate comparable galaxies. Curtis argued that the Milky Way is smaller, tens of thousands of light years, and that spiral nebulae are island universes, separate galaxies far beyond the Milky Way's borders, comparable in size and nature to our own galaxy, the universe containing countless such systems. The debate was partially about evidence and interpretation, both debaters presenting data supporting their positions, photographs and spectra and theoretical calculations, each side having reasonable arguments based on available information. Each Shapley pointed to Cepheid variable stars discovered in globular clusters, using their brightness relationships to calculate distances, showing these clusters were tens of thousands of light years away, implying a vast Milky Way system. Curtis noted that spiral nebulae showed spectra similar to stellar systems, that they rotated, that some showed dark dust lanes like those in the Milky Way, suggesting they were comparable objects at vast distances. The resolution would come not from debate but from better observations, more precise distance measurements, larger telescopes reaching fainter objects. The patient accumulation of evidence that characterizes scientific progress, theories tested against observation rather than settled by argumentation. The answer was already being worked toward even as the debate occurred, Edwin Hubble at Mount Wilson Observatory beginning the observational program that would settle the question definitively within a few years. Time moves forward again. You now find yourself at Mount Wilson Observatory in the mountains above Pasadena, California, in the year 1924. The observatory houses the largest telescope in the world, the 100-inch Hooker telescope, named after its benefactor John D. Hooker, the aperture allowing it to collect vastly more light than previous instruments, revealing objects too faint for smaller telescopes, pushing the observational frontier outward into deeper space. Imagine you're Edwin Hubble, lawyer turned astronomer, working on what would become one of the most important observational programs in astronomical history, attempting to measure the distances to spiral nebulae through detection and study of individual stars within them. A project requiring the world's largest telescope and perfect observing conditions. Years of patient work photographing the same nebulae repeatedly, building up data point by data point. The mountain setting is dramatic, Mount Wilson rising over 5,000 feet above sea level, above much of the atmospheric turbulence and water vapour that degrades seeing at lower elevations, the air thin and clean, the darkness profound when the moon is down, conditions perfect for deep photography of faint objects. The observatory domes are white against the dark sky, the largest housing the 100-inch telescope, a massive instrument requiring electrical motors to move its enormous weight smoothly, the technology of the day pushed to its limits to enable astronomical research. The observing begins at twilight, the dome shutters opening with their characteristic rumble, mechanical systems engaging, the telescope being prepared for the night's work, photographic plates loaded, the target coordinates calculated and set, the slow-motion drives engaged to track the sky's apparent rotation, compensating for Earth's spin. The smell of the mountain night is distinctive, pine trees covering the slopes, the air cool even in summer, thin enough that you notice the difference from sea level, breathing slightly deeper to get enough oxygen during physical work. Hubble's target tonight is the Andromeda Nebula, Messier 31, the largest and brightest spiral nebula visible from northern hemisphere, a fuzzy patch visible to naked eye as a faint smudge in the constellation Andromeda, resolved into a spectacular spiral structure in photographs, arms and dust lanes, and bright regions suggesting complexity. The question being whether it's a relatively nearby nebula within the Milky Way or a distant separate galaxy, an island universe, the debate still unresolved in 1924 despite years of observation and discussion. The photographic exposure begins, the plate holder sealed, the telescope tracking, hours passing as light from Andromeda accumulates on the emulsion. Photons travelling through space for hundreds of thousands of years now being captured, their energy triggering chemical changes in silver compounds, creating the latent image that development will reveal. Hubble monitors the guiding, watching a bright star in the guide telescope, making tiny corrections. The concentration required to maintain perfect tracking. The physical discomfort of the position, cold and fatigue competing with the importance of the work. The knowledge that each successful plate might contain crucial data. Dawn approaches, the eastern sky beginning to glow. The exposure ended, the plate removed and carried to the dark room for processing. The ritual of development, the image slowly appearing in the developing tray, the spiral structure of M31. Appearing, and critically, individual stars becoming visible. Bright stars that Hubble can measure and study, comparing plates taken on different nights to detect which stars vary in brightness. The technique allowing identification of Cepheid variables, special stars whose brightness varies periodically, the period being related to their intrinsic luminosity, allowing distance calculation. The discovery happens gradually, not a single revelation, but an accumulation of observations. Hubble finds Cepheids in M31, measures their periods, applies the period-luminosity relationship established by Henrietta Leavitt in her study of Cepheids in the Magellanic Clouds, calculates the distance to M31. The result is shocking, approximately 900,000 light-years, later revised upward to even greater distances as calibrations improved, but clearly far beyond the boundaries of the Milky Way system, definitively proving M31 is a separate galaxy, an island universe, settling the great debate in favour of Curtis's position. The philosophical impact is enormous, comparable to Copernicus removing Earth from the centre of the solar system, or Galileo's telescopic discoveries challenging Aristotelian cosmology. The Milky Way is not the entire universe, but just one galaxy among countless others, our cosmic home being ordinary rather than unique. The universe vastly larger than previously imagined, the implications profound for understanding cosmic scale and humanity's place within it. Hubble's work continues through the 1920s and 1930s, measuring distances to multiple spiral nebulae, all proving to be at vast distances, all being separate galaxies, the universe of galaxies revealing itself through patient observation and precise measurement, the landscape of the cosmos transforming from one giant Milky Way system to countless island universes scattered through space, the scale expanding by orders of magnitude, the human conception of the universe fundamentally reshaped by observational astronomy. The work happens in cycles, observing seasons when targets are optimally placed in the night sky, plate after plate exposed and developed and measured, patterns emerging from accumulated data, distances calculated and refined, errors identified and corrected. The slow, methodical progress of science, building understanding brick by brick, observation by observation. The Mount Wilson Observatory log books record thousands of nights of observations, the patient work of multiple astronomers, assistants, technicians, the collective effort required for major astronomical projects. No lone genius, but rather coordinated teamwork across years or decades. The smell of the dark room is familiar by now, photographer colleagues developing plates, the ritual of checking each one for quality, measuring positions of objects, recording data in logbooks, building databases of measurements, the repetitive work that makes up most of actual science, less dramatic than popular imagination suggests, but more systematic and rigorous, the foundation supporting occasional breakthrough discoveries. Remember those ancient Greeks wondering about the Milky Band? Remember Galileo resolving it into stars? Remember Herschel mapping its disk shape? Now Hubble proves that our galaxy is just one among billions, the progressive enlightenment spanning millennia, each generation building on the work of previous ones, each insight raising new questions, the journey from ancient mystery to modern understanding requiring patience and persistence and countless individuals contributing their efforts, the long, slow arc of scientific progress bending toward knowledge. The story continues beyond Hubble's discoveries, the understanding continuing to deepen through the 20th century and into the 21st. But the fundamental framework is now established. We live in a disc-shaped galaxy called the Milky Way, one of billions of galaxies scattered through an expanding universe, our cosmic address specified, our place in the larger structure known. The details remain to be worked out, the precise structure of the Milky Way's spiral arms, the nature of the galactic centre, the relationship between galaxies, the large-scale structure of the universe, questions for future investigation. But rest comes easier knowing that the mystery that puzzled ancient observers has been largely solved, that what appeared as a milky band of light has been understood as the combined glow of billions of stars in our home galaxy, that the patient work of astronomers across centuries has revealed our cosmic context, that human curiosity and ingenuity have proven adequate to understand even the vast scales of astronomical phenomena. Tomorrow, more observations will occur, more understanding will develop, more details will be filled in, the patient work continuing, the cycle of discovery persisting. The Milky Way turns slowly, completing one rotation every 230 million years. The stars orbiting the centre, the galaxy evolving on timescales almost incomprehensible to human experience, but now at least partially understood through the accumulated observations and calculations of those who devoted their lives to understanding our cosmic home. Decades have passed since Hubble's revelations about the universe of galaxies. You now find yourself in the post-war era of the 1940s and 1950s, when astronomy is being revolutionized not just by larger optical telescopes, but by entirely new ways of observing the cosmos, new windows opening onto phenomena invisible to human eyes, new technologies developed during wartime finding peaceful applications in scientific research, the radio spectrum revealing aspects of the universe that optical light cannot show. The challenge of mapping the Milky Way from inside it has remained stubborn. Optical telescopes, even the largest, can only see a few thousand light years through the disk before interstellar dust absorbs and scatters the light, creating an effective horizon, a wall of obscuration that makes the distant parts of the galaxy invisible. It's like trying to map a forest while standing at ground level on a foggy day, seeing only the nearest trees clearly, more distant ones becoming progressively hazier until they disappear entirely into the murk, the overall structure remaining mysterious despite patient observation. But radio waves, with wavelengths thousands of times longer than visible light, penetrate dust clouds with ease, passing through obscuring material that blocks optical light completely, allowing radio telescopes to map the entire galaxy, including regions hidden from optical view. The development of radio astronomy after World War II, using technologies developed for radar, opens this new observational window, revealing the galaxy in radio emission, particularly the 21 centimeter spectral line of neutral hydrogen, cold hydrogen gas permeating the galactic disk, its radio emission allowing detailed mapping of the galaxy's structure. Imagine you're a radio astronomer in the early 1950s working at one of the new radio observatories being established, perhaps Jodrell Bank in England, or the CSIRO facility in Australia, or the Dutch Radio Astronomy Institute, the field being young, the techniques being invented as you work, the excitement of pioneering a new form of astronomy competing with the frustrations of unreliable equipment and limited understanding of what you're detecting. The radio telescope is unlike anything used in optical astronomy. Instead of a polished mirror gathering light to a focus, it's a large dish or array of antennas collecting radio waves, the structure looking more like a radar installation than a traditional observatory, metal frameworks and wire mesh and electronic equipment. The whole system aimed at the sky, listening to cosmic radio emission, converting electromagnetic waves to electrical signals that can be amplified and recorded. The observing process is different from optical work. There's no eyepiece to look through, no photographic plate to develop. Instead, you monitor signals on chart recorders, pens tracing wiggly lines on slowly scrolling paper, the deflections indicating radio intensity at different frequencies, the visual representation of invisible electromagnetic waves, the translation of radio observations into forms human senses can comprehend. The sound is distinctive, the hum of electronic equipment, the whir of chart recorder motors, occasionally static from atmospheric interference, the technical environment of mid-century electronics, vacuum tubes glowing, transformers humming, the smell of warm electronics and ozone from high-voltage equipment. Your target is the 21 centimetre line of neutral hydrogen, discovered theoretically in 1944 by Hendrik van der Hulst, who predicted that hydrogen atoms should emit radio waves at this specific wavelength when the electron's spin flips from parallel to anti-parallel relative to the proton's spin, a quantum mechanical transition producing faint but detectable radio emission. The observation of this line in 1951 by Ewan and Purcell at Harvard and independently by Dutch astronomers confirmed the prediction and opened a new way to study the galaxy, neutral hydrogen being abundant throughout the galactic disk, its radio emission providing a tracer of the galaxy's structure. The beauty of the 21 centimetre line for galactic mapping is the Doppler effect. Hydrogen clouds moving toward or away from Earth show slightly shifted frequencies, the wavelength compressed or stretched by motion, allowing measurement of velocities. By scanning the galaxy and measuring the Doppler shifts of hydrogen emission in different directions, you can map not just where hydrogen is located, but how it's moving, the velocity information allowing construction of three-dimensional maps showing the galaxy's rotation and structure, inferring spiral arm locations from the patterns of motion and density. The work proceeds systematically, observing the galaxy direction by direction, recording the spectrum of hydrogen emission at each position. The receiver tuned to scan across frequencies near 1420 MHz, the natural frequency of the 21 centimetre line, detecting the Doppler shifted emission from hydrogen clouds moving at different velocities, measuring the shifts, calculating velocities from the known rest frequency, converting velocities to distances using models of galactic rotation, plotting the results on charts, showing galactic longitude and latitude, building up a comprehensive map through patient accumulation of observations over months and years. One night's observing session might cover a few degrees of the galactic plane, the telescope being pointed at a specific galactic longitude and latitude, the receiver locked onto the target, data collected for perhaps 5 or 10 minutes per position to achieve adequate signal-to-noise. Then the telescope moved to the adjacent position, the process repeated, the grid of observations slowly filling in, progress measured in positions completed rather than dramatic discoveries, the accumulation being methodical rather than exciting, most astronomy being routine data collection rather than eureka moments. The weather matters differently for radio astronomy than optical work. Clouds don't block radio waves, allowing observations even under overcast skies. The radio astronomer checking weather forecasts not for clouds, but for storms and high winds that might damage the antenna, lightning being particularly dangerous to sensitive electronics. Heavy rain sometimes causing signal degradation at shorter radio wavelengths, but 21 centimeters being long enough that rain has minimal effect. The advantage of radio being all-weather capability, maintaining productivity during seasons when optical telescopes sit idle under cloudy skies. The environment where you work develops its own rhythm and culture. The control room where you spend observing nights becomes familiar. The worn chair where you sit monitoring charts, the particular squeak of the door, the coffee maker that gurgles on a timer, the stack of technical manuals and journal articles on the shelf, the logbook where you record observations and note any problems. The accumulated character of a workspace used continuously over years, each observer contributing to the worn familiarity of shared scientific space. The conversations during observing runs with colleagues also working that night, discussions about data quality and instrumental problems and scientific interpretations. The social nature of research being important even in the solitary hours of monitoring equipment. The personal relationships that develop among people working together toward shared goals. The friendships and rivalries and collaborations that structure academic life. The human dimension of science being as important as the technical aspects, knowledge being socially constructed through communication and debate among researchers. The publications resulting from these surveys appear in the astronomical journals, Astrophysical Journal and Astronomy and Astrophysics, and monthly notices. The papers describing observations and analysis methods and results. The maps of hydrogen distribution, the interpretation in terms of galactic structure, the citations of previous work and comparison with other observations, the formal language of scientific papers conveying results to the wider community, each paper adding one small piece to the larger mosaic of understanding, most papers being incremental contributions rather than revolutionary breakthroughs, but the accumulation of incremental progress being how science advances, the collective effort of hundreds of researchers over decades producing comprehensive understanding. The environment where you work has its own character. The control room where you monitor observations smells of coffee and cigarette smoke, ashtrays overflowing. The culture of mid-century science being more casual about such things than modern safety-conscious institutions. The equipment racks line the walls, glowing vacuum tubes visible through ventilation grills. The warmth from all this electronics making the control room comfortable even on cold nights. The chart recorders produce long strips of paper that accumulate on the floor, later to be analysed and measured. The physical archive of radio observations, boxes of paper records documenting years of observations. The analysis happens later in offices during daytime, measuring the chart recorder traces, converting deflections to intensities and frequencies, calculating velocities from Doppler shifts, plotting positions on galactic coordinate maps. The tedious work of data reduction requiring care and patience, mistakes easily made, cross-checking necessary, the slow conversion of raw observations into scientific understanding. The scratch of pencil on graph paper, the click of mechanical calculators, the smell of coffee and paper, the routine of mid-century astronomical research, less romantic than popular imagination, but more methodical and rigorous. The results emerging from these radio surveys in the 1950s and 1960s reveal the Milky Way's spiral structure. The patterns of hydrogen emission, particularly the velocity patterns showing differential rotation, suggest that the galaxy has spiral arms similar to those visible in other galaxies. long curved structures where stars and gas concentrate, the arms winding outward from the central regions, the overall pattern resembling a pinwheel or a spiral shell, the disk not being uniform but having structure, regions of enhancement where stars form more actively, the architecture of our cosmic home slowly revealing itself. But determining exactly how many arms and where they are proves difficult. Different analyses using different assumptions about rotation curves and distance scales produce different maps, some showing 2 major arms, others 4. The exact structure remaining debated through the 1960s and 1970s, the uncertainty reflecting the fundamental difficulty of mapping a structure you're inside, analogous to a person wandering in a city trying to map the street layout without being able to see it from above, inferring structure from local observations, the bird's eye view that would make everything obvious being unavailable. Remember Herschel trying to map the galaxy by counting stars? Now radio telescopes map hydrogen gas throughout the entire galactic disk, seeing through the dust that limited optical surveys, the technological advance enabling more complete understanding, though challenges remain. The spiral arms gradually identified through multiple studies include the Perseus arm, Scutum Centaurus arm, Sagittarius arm, Norma arm, and importantly the Orion spur or local arm, the minor structure where the Sun is located, between the major Perseus and Sagittarius arms, our home being in a relatively minor feature rather than a major spiral arm, the pattern of discovery being that humans are never quite as centrally located or special as we might prefer, the Copernican principle applying at multiple scales. Years pass. You now find yourself in the 1970s and 1980s, attention focusing on the centre of the galaxy, that mysterious region hidden behind thousands of light years of dust in the constellation Sagittarius, invisible to optical telescopes but bright in radio and infrared wavelengths. Something energetic happening there, something worth investigating with the new technologies becoming available. Radio observations in the 1950s had detected a compact radio source at the exact centre of the galaxy, designated Sagittarius A, later refined to Sagittarius A star, SGR A star, to distinguish the compact core from extended emission in the region. The source is small, less than astronomical unit in size, based on radio interferometry measurements, incredibly compact compared to the scale of the galaxy, and bright, emitting powerfully at radio wavelengths despite being point-like, the characteristics suggesting something unusual, perhaps the remnant of a supernova or something even more exotic. Infrared observations pioneered in the 1960s and advancing rapidly in the 1970s with better detectors and techniques can also see through dust, revealing dense clusters of stars near the galactic centre. The central parsec containing millions of stars packed into a volume where the nearest star to the Sun is several light years away, the density contrast being enormous, the inner galaxy being a much more crowded stellar environment than our local neighbourhood. Imagine you're an infrared astronomer in the late 1980s, working at an observatory equipped with new infrared cameras, perhaps Mauna Kea in Hawaii, where high-altitude telescopes operate above much of the atmospheric water vapour that absorbs infrared light, observing the galactic centre region, attempting to study the stars near SGR A star, measuring their positions and motions, building up a census of the central stellar population. The infrared observing has its own challenges and techniques, different from both optical and radio work, requiring different equipment and different approaches to data collection. Infrared detectors must be cooled to very low temperatures, often to liquid nitrogen temperatures around 77 Kelvin, or even colder using liquid helium, to reduce thermal noise that would otherwise overwhelm the faint signals from distant astronomical objects. The detector itself being warm enough at room temperature that its thermal emission would be far brighter than the objects being studied, analogous to trying to observe faint stars during daytime, the cooling being essential for sensitivity. The liquid nitrogen cooling systems require regular filling, dews being topped up every few hours during observing, the hiss of boiling nitrogen as the cryogenic liquid evaporates being a familiar sound in infrared observatories, the careful handling of dewars containing coolant at temperatures that would cause instant frostbite, the heavy protective gloves worn when pouring, the clouds of condensed water vapour forming in the air around the cold equipment, the visible manifestation of the temperature differential, the practical challenges of maintaining cryogenic systems through observing runs lasting many nights. The detectors at this time, the late 1980s and early 1990s, are less sensitive than modern devices, requiring longer exposures to achieve adequate signal-to-noise ratios, integration times of several minutes per image being typical, much longer than optical. CCDs can accumulate before saturation, the patience required for infrared observations being even greater than optical work. Though the technology is advancing rapidly, new detector arrays becoming available every few years, sensitivity improving, observing times decreasing, the field being in a growth phase, exciting opportunities but also frustration as equipment becomes obsolete quickly. The field of view of infrared cameras is often small, perhaps a few arc-minutes or less, seeing only a tiny portion of the sky at once, building up a complete image of the galactic centre requiring multiple pointings with careful positioning. The individual frames later combined into mosaics, the process requiring precise telescope pointing and tracking, any errors causing misalignments in the final mosaic, the data reduction being complex, matching overlapping regions, correcting for different sensitivity across the detector, removing cosmic ray hits and bad pixels, the processing pipeline being developed as observations proceed, no standard software existing, every research group developing their own tools. The dome environment during infrared observing feels similar to optical observing in many ways, the same rhythm of preparing for the night as twilight fades, the dome opening with its characteristic rumble, cool night air flowing in, bringing the smell of the mountain, pine trees on the slopes of Mauna Kea, the elevation being over 4,000 meters, the thin air making physical work difficult, every movement requiring more effort at altitude, observers sometimes using supplemental oxygen, the physiological challenges of high-altitude work adding to the technical demands. The observing itself involves pointing the telescope at the target coordinates, waiting for the telescope's computer to slew the instrument into position, fine-tuning the pointing using bright stars or the target itself if visible, starting the exposure sequence, monitoring the system to ensure everything is working properly, the detector cooling, holding steady, the telescope tracking accurately, the data quality being acceptable, then waiting as photons accumulate, minutes passing, the exposure counter showing progress, finally reading out the detector, transferring the data to disk, examining the image on the display screen to verify that the target was captured successfully, then moving to the next position in the mosaic pattern, the cycle repeating. The data looks different from optical images. Infrared observations showing heat rather than visible light, cool stars that are faint optically appearing bright in infrared, hot blue stars that dominate optical images fading in infrared, dust clouds that block optical light glowing with thermal emission in infrared, a different view of the same sky, complementary information revealing aspects invisible at other wavelengths, the multi-wavelength approach being essential for complete understanding, different wave bands providing different insights into physical processes. The analysis happens in the following days and weeks after observing runs, back at the home institution, processing the raw data, applying flat field corrections to remove pixel-to-pixel sensitivity variations, sky subtracting to remove the bright thermal emission from Earth's atmosphere, combining multiple exposures to increase signal-to-noise and build up the final mosaics, measuring star positions precisely using centroiding algorithms, calibrating the brightness scale using standard stars with known infrared magnitudes, converting the instrumental measurements to physical units, producing catalogues of detected stars with positions and brightnesses and colours. The database is growing as more observations are added over subsequent years. The long-term monitoring programs tracking stars near the galactic centre require observations spanning many years, each observing season adding new position measurements for tracked stars, the motions being detected by comparing positions from different epochs, the proper motions being measurable despite the enormous distance, because stars very close to Sagittarius, A star, are moving so fast, orbital velocities reaching thousands of kilometers per second, translating to angular motions of several milliarc seconds per year, detectable with careful astrometry. The patience required for such programs being extraordinary, graduate students starting projects that won't yield complete results until after their PhDs, postdocs working on multi-year datasets. The long-term commitment necessary for measuring orbital periods that are decades long. The breakthrough observations come in the 1990s and 2000s through long-term monitoring programs, particularly the work of Andrea Ghez at UCLA using the Keck telescopes, and Reinhard Genzel's group at the Max Planck Institute using the Very Large Telescope in Chile, both teams tracking individual stars in the central light year for over a decade, measuring positions with increasing precision as adaptive optics technology improves, building up orbital solutions for stars moving around whatever is at the exact centre. One star, designated S2 or S0-2 depending on the catalogue, becomes particularly important. It has a short orbital period of about 16 years, allowing multiple observations around its orbit, and it approaches very close to SGR-A star at periastron within a few light days, moving at incredible speeds exceeding 5,000 kilometers per second at closest approach, roughly 2% of the speed of light, velocities requiring enormous gravitational force to maintain the orbit. Imagine watching the data accumulate over years, each observing season adding new position measurements, the pattern of motion becoming clearer, the elliptical orbit emerging from the data points, the application of Kepler's laws allowing calculation of the central mass from the orbit's size and period. The result is unavoidable. Approximately 4 million solar masses concentrated within a region smaller than the solar system's inner planets. The only explanation consistent with all observations being a supermassive black hole, SGR-A star being not a cluster of stars or an exotic object but a black hole, whose event horizon is only about 12 million kilometers across, tiny compared to the galaxy, but massive beyond comprehension. The work earning the 2020 Nobel Prize in Physics, shared by Ghez and Genzel, along with Roger Penrose for theoretical work on black holes, the recognition that their patient multi-decade observational programs had definitively proven the existence of the supermassive black hole at our galaxy's centre, the validation of theoretical predictions through careful empirical work, the pattern of science at its best, theory and observation working together to understand the cosmos. Scholars still debate exactly how supermassive black holes form, whether through direct collapse of massive gas clouds in the early universe, through mergers of smaller black holes growing over cosmic time, through the collapse of very massive stars that formed before the universe enriched with heavy elements, the formation mechanism remaining uncertain despite the established fact that such black holes exist at the centres of most large galaxies, including our own. You now find yourself in the modern era, the late 20th and early 21st centuries, when understanding of the Milky Way has become quite detailed, when professional galactic astronomy has become a career path for hundreds of astronomers worldwide, when large surveys and space missions have accumulated data on billions of stars, when computational power allows complex simulations of galactic dynamics, when the patient work of many generations has built a comprehensive picture of our cosmic home. The everyday life of galactic astronomers follows patterns similar to other fields of research. Imagine you're a professor at a university, your research focusing on galactic structure, your time divided between teaching, research, writing grant proposals, attending conferences, advising students, the many demands of academic life in the modern era. The rhythm of your year follows the academic calendar, but also the observing seasons. Telescope time is precious and must be applied for. Proposals written describing what you want to observe and why it matters. Review panels evaluating proposals and awarding time to the most scientifically valuable projects. The competition being intense, typical success rates perhaps 20 to 30%, meaning most proposals are rejected, requiring persistence and resilience, resubmitting proposals with improvements, waiting months for decisions, the cycle of applications and rejections, and occasional successes that structures much of astronomical research. When you receive telescope time, the preparations begin weeks in advance, preparing observing scripts, calculating optimal exposure times, coordinating with colleagues if the project is collaborative, making travel arrangements if the telescope is at a remote observatory. The logistics of modern astronomy being complex, especially for major facilities in places like Chile or Hawaii, international travel and time zone adjustments, and the physical demands of nighttime work at high altitude. The observing run itself might last several nights, flying to the observatory location, adjusting to the altitude if it's a mountain site, meeting with telescope support staff, being trained on current observing procedures, spending nights in the control room, monitoring as the automated systems execute your observing program, robotic telescopes having largely replaced hands-on guiding, except at some older facilities, the process being more about monitoring than direct control, though problems still require human intervention and decision-making. The data collected might be gigabytes or terabytes, depending on the project, downloaded from the telescope's computer systems, copied to hard drives for transport home, backed up carefully because data loss would mean wasted telescope time, impossible to replace if observations can't be repeated. The modern astronomical data pipeline involves substantial computing infrastructure, powerful workstations or computing clusters for data processing, specialized software for reducing and analyzing observations, the technical skills required for modern astronomy, including programming and data science, the field having evolved from the era of individually examining photographic plates to processing millions of spectra automatically. The analysis phase takes months or years depending on project complexity. Data reduction, removing instrumental effects, calibrating to standard photometric or spectroscopic systems, measuring positions or velocities or brightnesses of objects, comparing with theoretical models, iterating when initial analyses reveal problems, the gradual refinement of understanding through careful work, the slow progress from raw data to scientific conclusions, most research taking far longer than popular imagination suggests, papers representing years of effort rather than sudden breakthroughs. The collaboration is extensive, modern astronomy rarely being solitary work. Research groups including postdocs and graduate students and undergraduate assistants, international collaborations connecting researchers across continents, teleconferences, and email replacing letters as communication methods. But the social nature of science continuing, ideas refined through discussion, errors caught through peer review, understanding emerging from collective effort rather than individual genius. The grant writing consumes significant time, funding agencies requiring detailed proposals describing planned research, justifying its importance, demonstrating feasibility, budgeting equipment and personnel costs, the financial infrastructure supporting modern science being complex, government agencies and private foundations providing funding, universities managing grants, administrators tracking expenditures, the bureaucracy sometimes feeling oppressive, but enabling the expensive infrastructure astronomy requires, the balance between scientific freedom and accountability being ongoing negotiation. Time moves forward. The understanding of the Milky Way's structure becomes increasingly detailed through comprehensive surveys and space missions. The Milky Way is now known to be a barred spiral galaxy, the central region having a bar-shaped distribution of stars rather than a simple spherical bulge. The bar being roughly 27,000 light-years long, oriented so that one end points roughly toward us, the bar rotating at its own rate, feeding gas toward the centre, affecting spiral arm structure, a major architectural feature revealed through detailed mapping. The spiral structure includes 4 major arms: the Scutum Centaurus arm, the Carina Sagittarius arm, sometimes called the Sagittarius Carina arm, the Perseus arm, and the Norma Cygnus arm, also called the outer arm, though the exact number and nomenclature remains somewhat debated, some models combining certain features differently, the complexity of real galactic structure not fitting perfectly into simple schematic diagrams, reality being messier than textbook illustrations. The Sun's location is well established now. In the Orion spur, a minor arm sometimes called the local arm, between the Perseus and Sagittarius arms, approximately 26,000 light-years from the galactic centre, about halfway out along the galactic radius, the galactic disk being roughly 100,000 light-years in diameter, our position being neither central nor peripheral, but intermediate, ordinary, a typical location within the galactic disk. The galactic rotation at the Sun's position takes approximately 230 million years to complete one orbit. The last time the Sun was at its current position relative to the galaxy's centre was during the Triassic period, when dinosaurs were just emerging, a galactic year being vastly longer than human history, or even the entire span of human evolution, the timescales of galactic dynamics dwarfing those of terrestrial life. Yet the galaxy has completed about 50 orbits since its formation, time enough for significant evolution of structure. The galaxy's components are now understood in detail. The thin disk where the Sun resides contains young stars and gas, the star-forming regions and OB associations and open clusters, the spiral arms being enhanced regions within this disk, the thickness being roughly 1,000 light-years. The thick disk contains older stars, less gas, greater thickness of a few thousand light-years, possibly formed through heating of the thin disk or accretion of disrupted satellites. The stellar populations having different characteristics, different kinematics, the galaxy being layered rather than uniform. The central bulge, once thought spherical, is now known to be peanut-shaped when viewed edge-on, actually the vertical projection of the bar viewed from our position. The three-dimensional structure being complex, stellar orbits arranged in a way that creates the bar, the dynamics being products of gravitational interactions and resonances, N-body simulations on supercomputers successfully reproducing the observed structure, theory, and observation agreeing. The dark matter halo remains mysterious, detected only through gravitational effects, rotation curves of the galaxy staying flat at large radii rather than declining, as expected from visible matter alone, the inference being that dark matter extends far beyond the visible disk, the dark matter mass being perhaps 5 times the visible stellar and gas mass, the galaxy being mostly invisible, the visible stars being a minority component embedded in a vast dark halo, the nature of dark matter remaining one of astronomy's great unsolved problems. Globular clusters orbit in the halo. Over 150 known ancient stellar populations formed early in the galaxy's history, each cluster containing hundreds of thousands of stars in a compact sphere. The globular clusters moving on high inclination orbits, taking them far above and below the galactic plane. Their dynamics tracing the gravitational potential of the entire galaxy, including the dark matter halo. Remember Galileo seeing the Milky Way as countless stars? Now we measure positions and velocities of over 1 billion individual stars, the scope of understanding expanding by factors of millions, the patient accumulation of knowledge spanning centuries. The Gaia satellite, launched by the European Space Agency on December 19, 2013, on a Soyuz rocket from French Guiana, represents the culmination of decades of planning and development. The mission concept dating back to the 1990s, the technical challenges being immense, requiring advances in multiple areas, from spacecraft design to detector technology to data processing algorithms, the investment being substantial, over €1 billion, but the scientific return justifying the cost, the mission transforming multiple fields of astronomy in ways that will continue for decades. The spacecraft orbits the Sun-Earth L2 Lagrange point, approximately 1.5 million kilometers from Earth on the side away from the Sun, a gravitationally stable location where the spacecraft can maintain its position with minimal fuel consumption, allowing mission lifetime limited by other factors rather than propellant, the orbit being carefully designed for optimal observing conditions, avoiding Earth's shadow and maintaining constant solar illumination for power and thermal stability. Gaia slowly spins at a rate of 1 revolution every 6 hours, the rotation allowing its 2 telescopes to continuously scan great circles across the sky, the spin axis being oriented perpendicular to the Sun direction, the geometry carefully chosen so that each region of sky is observed multiple times from different angles over the mission lifetime. The multiple observations allowing precise astrometry through triangulation, the redundancy also providing robustness against instrumental problems or cosmic ray hits on individual measurements. The telescopes themselves are remarkable instruments, 2 identical optical systems sharing a single focal plane, each with aperture of 1.45 by 0.5 meters, rectangular rather than circular to optimize the scanning geometry, the optics being silicon carbide, a material chosen for its thermal stability and lightweight properties. The entire optical system being thermally isolated and maintained at constant temperature to prevent thermal distortion that would degrade astrometric precision, the engineering being state-of-the-art, pushing multiple technologies to their limits. The focal plane contains 106 CCDs arranged in a rectangular array, the largest and most complex camera ever built for space astronomy at the time, each CCD being read out continuously as stars drift across it due to the spacecraft's rotation, the time-delayed integration mode allowing long effective exposures while scanning, the data rate being substantial hundreds of megabits per second compressed on board before transmission to Earth, the telecommunications link being a limiting factor requiring careful data management and prioritization. Imagine yourself in the Gaia Mission Operations Center at ESOC in Darmstadt, Germany, monitoring the satellite's health and status, the control room filled with workstations showing telemetry displays, spacecraft engineers monitoring subsystems, mission planners coordinating activities, data processing specialists ensuring that science data is being received and archived properly. The 24-hour operations requiring shift work, teams rotating through day and night coverage, the continuous vigilance necessary for successful space missions. The routine operations are mostly automated, the spacecraft executing pre-programmed scanning sequences, collecting data, transmitting to ground stations, the human operators monitoring for anomalies, ready to intervene if problems arise but usually observing nominal operations, the reliability of space hardware being generally high once on-orbit problems are resolved, though occasional issues require troubleshooting and sometimes uploading software patches or changing operational procedures, the mission being a living system requiring ongoing care and attention. The data flows continuously to ground stations, the Deep Space Network antennas in Spain and Argentina receiving Gaia's transmissions, the raw telemetry being forwarded to the data processing center, the automated pipelines converting raw measurements to astrometric solutions, the processing being computationally intensive, requiring supercomputers and distributed computing resources, thousands of CPU cores working in parallel to process the flood of observations. The challenge being not just collecting data, but processing it into useful scientific products. The Gaia Data Processing and Analysis Consortium, DPAC, involves over 400 scientists and software engineers from institutions across Europe. The collaborative effort being essential for handling the data complexity. Different working groups specializing in various aspects: photometry, spectroscopy, radial velocity, variable stars, solar system objects, each producing specialized catalogues, the integration of all these data products requiring careful coordination and cross-validation, the organizational challenge being as significant as the technical ones. The data releases come at intervals after launch, allowing time for calibration and validation. The first data release in September 2016, containing positions for over 1.1 billion stars. The second release in April 2018, adding proper motions and parallaxes and colours for 1.3 billion stars, plus radial velocities for a subset. The third release in December 2020, expanding further. Each release being a major event in astronomy, the data being made publicly available immediately, enabling researchers worldwide to use it. The open data policy being part of ESA's scientific culture, maximising the return on the investment by allowing global participation in analysis. The scientific papers using Gaia data number in the thousands already, and will eventually number in the tens of thousands, every paper acknowledging the Gaia mission, and DPAC, the citation count growing exponentially, the mission's impact being visible in publication statistics. Topics ranging from stellar astrophysics to galactic structure to solar system dynamics to fundamental physics tests. The breadth of applications being remarkable, the precision astrometry enabling insights in multiple fields, the mission exemplifying how infrastructure investments in basic research produce unpredictable but valuable returns. Gaia reveals fine structure in the galaxy that was invisible in previous surveys, stellar streams from disrupted dwarf galaxies, thin rivers of stars orbiting the Milky Way, the tidal debris from satellites that ventured too close and were torn apart by gravitational forces, the streams tracing out past merger events, the archaeology of the galaxy's formation history being written in these streams, patience analysis of phase space distributions revealing patterns invisible to casual inspection, the power of large statistical samples and precise measurements. Moving groups and kinematic substructure appear in velocity space, stars moving together suggesting they formed in the same molecular cloud and are still loosely associated despite having dispersed across the sky, the shared motion being detectable with Gaia's proper motion measurements, allowing identification of coeval populations, reconstructing star formation history, understanding how stellar clusters disperse over time, the connection between stellar kinematics and formation environments. Remember those ancient observers watching the Milky Band, wondering what it was? Now satellites measure positions and velocities of 1 billion stars within it, the scope of understanding expanding by factors of millions, the progress from naked eye to Gaia spanning millennia but producing comprehensive knowledge, the patient accumulation of observations and instruments and theories and analyses building a detailed picture of our cosmic home, humanity's collective project of understanding the universe yielding fruit through sustained effort across generations. Quirky detail. Gaia measures not just position, but also proper motion and parallax for each star, allowing 3-dimensional mapping and full 6-dimensional phase space positions when combined with radial velocity. The complete kinematic information enabling detailed dynamical studies, tracing orbits backward and forward in time, identifying stars that were born together but have since dispersed, reconstructing the galaxy's history through forensic analysis of stellar trajectories. The debates continue about various details, the exact pattern of spiral arms, whether they are material arms or density waves, whether the bar is long or short compared to other barred galaxies, how the bar formed and how it influences the galaxy's evolution, whether there are rings or pseudo-rings, how the dark matter halo is distributed, whether the halo is spherical or triaxial, questions that remain active research topics, the understanding continuously refined but never final, science being an ongoing process rather than a completed edifice. The story continues into the future, new missions being planned, new telescopes being built, new questions being formulated as old ones are answered, the cycle of discovery persisting. But rest comes easier knowing that the basic structure of our cosmic home is now well understood, that centuries of patient observation and careful analysis have revealed the Milky Way's architecture, that we know where we are and what we're inside of, the mystery that puzzled ancient observers having been largely solved through human curiosity and effort. Tomorrow more data will arrive, more patterns will be found, more details will be filled in, but the fundamental picture is established, our galactic context known, our cosmic address specified with precision. You now find yourself understanding the Milky Way, not in isolation but as part of a cosmic neighbourhood, a member of a small group of galaxies bound together by gravity, slowly orbiting their common centre of mass, the local group of galaxies, perhaps 50 or 60 members, depending on where you draw the boundaries, most being small dwarf galaxies, but 3 being substantial spiral systems. The Milky Way being one of the 2 largest, our cosmic context extending beyond our own galaxy to include our immediate galactic neighbours. The local group spans approximately 10 million light-years, a small volume in cosmic terms, isolated from other galaxy groups by tens of millions of light-years of nearly empty space. The structure being gravitationally bound, the member galaxies orbiting rather than participating in the general cosmic expansion, local gravity overcoming the expansion on these scales, the group being a self-contained system within the larger expanding universe. The largest member is the Andromeda Galaxy, Messier 31, visible to naked eyes from dark sites in the northern hemisphere as a faint smudge in the constellation Andromeda, actually larger than the Milky Way by some measures, containing perhaps 1 trillion stars compared to our few 100 billion, though mass estimates are uncertain and depend on dark matter content. The two galaxies being comparable in scale, neither clearly dominant, twin spirals separated by 2.5 million light-years of space. Imagine observing Andromeda from a dark site, perhaps a desert or mountain location far from city lights, on a moonless autumn night when the galaxy is high in the sky. The naked eye perception is of a faint fuzzy patch, unremarkable unless you know what you're looking at. The photons entering your eye having travelled for 2.5 million years, having left Andromeda when early hominids walked Earth, the light being ancient by human standards but instantaneous in cosmic terms. The connection between observer and observed being direct. Photons travelling unimpeded across intergalactic space to trigger chemical reactions in your retina. Through binoculars or a small telescope, Andromeda's structure becomes visible, the bright core and the dimmer disk extending outward, the spiral arms requiring large telescopes and long exposures to photograph, but the overall elliptical shape apparent even in modest instruments. The galaxy subtending several moon widths on the sky despite being incredibly distant, the angular size reflecting both genuine physical size and relative proximity. Andromeda being close enough and large enough to show substantial apparent size. The third major local group member is the Triangulum Galaxy, Messier 33, smaller than either the Milky Way or Andromeda, perhaps 50 billion stars, a face-on spiral visible in binoculars under good conditions, fainter than Andromeda, and more difficult to observe, but still a naked eye object under ideal dark sky conditions. The third spiral in our small group, the three large galaxies dominating the local group's dynamics, their combined gravity binding the smaller members. The rest of the local group consists of dwarf galaxies, small stellar systems containing millions to billions of stars rather than hundreds of billions, orbiting as satellites around the three large spirals. The Milky Way and Andromeda each having their own retinue of satellites, the dwarfs being much more numerous than major galaxies, the population of small galaxies vastly exceeding large ones, the universe containing far more dwarf galaxies than spirals and ellipticals, though the large galaxies contain most of the stars. The Milky Way's most prominent satellites are the Magellanic Clouds, visible from the southern hemisphere as detached portions of the Milky Way, two irregular dwarf galaxies orbiting our galaxy, containing billions of stars each, large enough to be naked eye objects, known to ancient southern observers but not studied telescopically until European exploration of the southern hemisphere in the Age of Discovery, named after Ferdinand Magellan, though known to indigenous peoples for millennia before his voyage. Imagine yourself in Chile or Australia or southern Africa, at a dark site with clear skies, observing the night sky in the southern hemisphere. The Milky Way arches overhead as it does in the north, but the southern Milky Way is brighter, the view toward the galactic centre being in southern constellations, the richest star fields visible from southern latitudes. And floating near the Milky Way, detached from the main band but clearly associated, are two cloudy patches, the large Magellanic Cloud and small Magellanic Cloud, LMC and SMC, glowing softly, resolved into individual stars in binoculars, the irregular structure apparent even to naked eyes, the feeling being that you're seeing neighbouring galaxies, island universes close enough to appear substantial. The Magellanic Clouds are being affected by the Milky Way's gravity, their orbits bringing them close to our galaxy, tidal forces beginning to disrupt their structure, stars being pulled from the dwarfs by gravitational interaction. The Magellanic Stream being a long trail of hydrogen gas stripped from the clouds by tidal forces, wrapping around the Milky Way, evidence of ongoing gravitational interaction. The slow process of the Milky Way cannibalizing its satellites, growing by accretion. The cycle of galactic evolution involving mergers and disruption of smaller systems. Radio observations in the 1970s discovered the Magellanic Stream, neutral hydrogen emission tracing a filament extending over 100 degrees across the sky, connecting the clouds to the Milky Way's outer halo, the gas being slowly accreted, eventually forming new stars in the Milky Way's disk, the material from the clouds contributing to our galaxy's continued evolution, the cycle of destruction and renewal, satellite galaxies being torn apart but their material being recycled, nothing being truly lost, just redistributed. Other Milky Way satellites are smaller and fainter, discovered through systematic surveys of the sky, searching for overdensities of stars, concentrations suggesting bound stellar systems rather than random fluctuations. The Sagittarius dwarf elliptical galaxy was discovered only in 1994, despite being one of the closest external galaxies, approximately 70,000 light-years from Earth, hidden behind the dense star fields of the galactic bulge, its member stars being difficult to distinguish from Milky Way stars in the same direction. The discovery requiring careful analysis of stellar populations, colour magnitude diagrams revealing a population distinct from foreground Milky Way stars. Sagittarius dwarf is being torn apart by Milky Way tidal forces, its stars being pulled into long streams wrapping around our galaxy, the disruption being advanced, the dwarf already having passed through the galactic disk multiple times, each passage stripping more stars. The eventual fate being complete disruption, the satellite being entirely absorbed into the Milky Way's halo, contributing its stars to our galaxy's population. The process of galactic cannibalism happening in real time, observable in current surveys. Dozens of ultra-faint dwarf galaxies have been discovered in recent years through surveys like the Sloan Digital Sky Survey and subsequent dedicated searches, tiny systems containing only thousands or tens of thousands of stars, the faintest galaxies known, requiring large telescopes and careful analysis to detect. The discoveries enabled by modern surveys covering large areas of sky with sufficient depth to reveal these elusive objects, each discovery adding to the census of local group members, the population being much richer than previously imagined. The ultra-faint dwarfs are interesting theoretically because their number and properties relate to dark matter physics, simulations of galaxy formation predicting specific populations of small satellites. The observations testing these predictions, the match or mismatch between theory and observation constraining models. The small-scale structure of dark matter halos being revealed through satellite populations. The tension between predicted and observed satellite numbers being an active area of research, the missing satellites problem, or too big to fail problem, suggesting our understanding of dark matter or galaxy formation requires refinement. Dark matter itself remains mysterious despite its importance for understanding galaxies, one of the profound puzzles in modern physics, the existence being well established through multiple independent lines of evidence, but the fundamental nature remaining unknown despite decades of theoretical and experimental work. The evidence for dark matter in the Milky Way comes from multiple observations converging on the same conclusion. the rotation curves being perhaps the most compelling, measuring the orbital velocities of stars and gas at various distances from the galactic centre, plotting velocity versus radius, the pattern revealing something unexpected and profound. The rotation curve measurements come from diverse tracers, each providing velocity information at different galactic radii. In the inner regions within a few kiloparsecs of the centre, individual stars' radial velocities measured spectroscopically provide data points, the Doppler shifts of stellar absorption lines revealing how fast stars orbit. At intermediate radii where the Sun is located, local stellar velocities, combined with proper motion measurements from Gaia, provide complete three-dimensional velocities for millions of stars. Statistical analysis revealing the circular velocity at the Sun's position being approximately 220 kilometers per second, sometimes quoted as 230 or 240 depending on analysis details. The uncertainty being surprisingly large despite precision measurements, reflecting systematic uncertainties in distance scale and modelling assumptions. At large radii beyond the optical disk, neutral hydrogen 21 cm emission provides velocity tracers, the hydrogen gas forming an extended disk reaching farther than stars, the rotation curve being measurable to distances of perhaps 50,000 light-years or more, the outer regions being crucial for understanding dark matter, because that's where dark matter dominates over visible matter most strongly, the outer rotation curve being most sensitive to total gravitational mass, including the dark component. The expectation from visible matter alone, from the stars and gas we can observe, is that orbital velocity should decline at large radii following Kepler's laws, the same mathematics governing planetary orbits around the Sun applying to stars orbiting the galactic centre, velocity being inversely proportional to the square root of radius at distances beyond most of the mass, producing a declining rotation curve at large radii, velocity decreasing as radius increases, the pattern being what Newtonian gravity predicts for a system where most mass is concentrated toward the centre. But observations show velocity remaining nearly constant or flat at large distances rather than declining, the rotation curve staying at roughly 200 to 250 kilometers per second out to the farthest measured distances, perhaps even rising slightly in some analyses. Though this remains debated, the flatness being inconsistent with visible matter alone, requiring additional mass not emitting or absorbing electromagnetic radiation. Invisible mass detected only through gravitational effects, the dark matter whose distribution must be inferred from the rotation curve, discrepancy, and other observations. Imagine examining rotation curve data, plots showing velocity versus radius, the measurements coming from observations of stars and gas at various distances from the galactic centre, 21 centimetre hydrogen observations extending to large radii, individual star velocities from spectroscopy providing points at intermediate distances, the combined data revealing the pattern, velocity rising in the inner regions as expected, reaching maximum around the Sun's orbit, then remaining flat rather than declining, the flatness requiring dark matter dominating the mass at large radii. The distribution of dark matter in the Milky Way's halo can be modelled, fitting observations to theoretical density profiles, the Navarro-Frenk-White profile, or other models describing how dark matter density varies with radius, the central density and scale radius being parameters determined from observations, the total dark matter mass within the virial radius being estimated at several trillion solar masses, 5 to 10 times the visible stellar and gas mass, the galaxy being mostly dark matter by mass, the luminous component being a relatively small fraction embedded in a vast dark halo. The nature of dark matter remains unknown, one of cosmology's great unsolved problems. The leading hypothesis is weakly interacting massive particles, WIMPs, hypothetical particles that interact gravitationally but not electromagnetically, making them invisible but detectable through gravitational effects. Numerous experiments searching for direct detection of dark matter particles, deep underground detectors shielded from cosmic rays, waiting for rare interactions between dark matter particles and detector atoms. So far, without confirmed detection, the parameter space being gradually constrained, ruling out certain masses and interaction cross-sections, but not eliminating the possibility. Alternative hypotheses include axions, lighter particles, proposed for other reasons in particle physics, or primordial black holes formed in the early universe, or modifications to gravity rather than new particles. The Mond hypothesis, suggesting gravity behaves differently at low accelerations, reproducing rotation curves without dark matter. Though Mond has difficulties explaining other observations like gravitational lensing and large-scale structure, the weight of evidence favouring dark matter particles over modified gravity, but the question remaining open pending direct detection or other definitive evidence. The scholarly debate continues about dark matter's exact properties and distribution, whether halos are spherical or triaxial, whether there are substructures or if the halo is smooth, whether dark matter self-interacts or is purely collisionless, questions that high-resolution simulations and improved observations are gradually addressing, the understanding refining but fundamental mysteries remaining, the placeholder dark matter standing for something real whose ultimate identity we don't yet know. Time flows forward in your imagination, decades and centuries and millennia, millions of years passing, the perspective shifting to cosmic timescales, where human history becomes a brief moment, where even the rise and fall of civilizations happens in an eye blink, where the significant changes are motions of galaxies and evolution of stellar populations, the long, slow dance of cosmic structures playing out over times almost incomprehensible to human experience. The Milky Way and Andromeda are approaching each other, their mutual gravitational attraction pulling them together, despite the general expansion of the universe, the local group being gravitationally bound, the two largest members falling toward their common centre of mass, the approach happening slowly by human standards but rapidly by cosmic ones. Velocities of approximately 110 kilometers per second, bringing the galaxies together, the distance decreasing, the eventual interaction being inevitable, the future being written in the current motions. For many years the prediction was that Andromeda and the Milky Way would collide in approximately 4 to 5 billion years, the galaxies merging to form a larger elliptical galaxy, the collision being dramatic despite galaxies being mostly empty space, stars rarely colliding but orbits being scrambled by gravitational interactions, gas clouds colliding and forming new stars, the morphology transforming from two spirals to one elliptical, the outcome being well studied through simulations of galaxy mergers. But more recent observations, particularly measurements from the Hubble Space Telescope and Gaia satellite determining Andromeda's tangential velocity, its sideways motion across the sky, have revised the prediction. Andromeda is not heading directly toward us, but has significant sideways motion, the trajectory being more complex than a simple head-on collision, the calculations suggesting approximately 50% probability of direct merger. The other possibility being a near miss where the galaxies pass close but don't immediately merge, perhaps requiring multiple close approaches before final coalescence, the uncertainty reflecting measurement uncertainties in Andromeda's proper motion, the tangential velocity being small and difficult to measure precisely even with the best instruments. Additionally, the Large Magellanic Cloud may influence the interaction, recent simulations suggesting the LMC's gravity affects the Milky Way's motion, potentially changing the relative velocity and geometry of the Milky Way-Andromeda encounter. The three-body problem being complex, outcomes being sensitive to initial conditions, small changes in trajectories producing different results. The future being genuinely uncertain rather than predetermined, multiple possible outcomes existing, the particular path taken depending on details we don't yet know precisely. Imagine the encounter in excessive, sleep-inducing detail, the kind of slow description that lulls rather than excites, the patience necessary for contemplating events billions of years in the future, time scales so vast that the Earth will no longer exist as a habitable world, the Sun having expanded into a red giant, the inner planets being engulfed or rendered lifeless, the future being abstract rather than experiential, something to contemplate intellectually rather than witness directly. The approach takes billions of years, the galaxies slowly growing larger in each other's skies, Andromeda becoming a prominent naked eye object, then dominating the night sky, the spiral structure becoming visible to unaided eyes, individual bright stars and nebulae resolving, the view being spectacular if any observers exist to see it, the approaching galaxy filling larger and larger portions of the sky, the realization that collision is imminent. The first close approach happens perhaps 4 billion years from now, the exact timing depending on current velocities and the gravitational influences of other local group members. The galaxies passing through each other, not colliding in the sense of solid objects impacting, but interpenetrating, stars passing between stars of the other galaxy, space between stars being so vast that actual stellar collisions are extremely rare. Probability calculations showing that very few, if any, stars would directly impact despite billions of stars being involved. But gravitationally the interaction is dramatic, each galaxy's gravitational field affecting the other, stars' orbits being perturbed, some stars being flung to large distances, forming tidal tails, long streams of stars pulled from the galaxies by tidal forces. The characteristic features of galaxy mergers visible in many interacting systems observed at various stages of merger, the local group collision following patterns seen in other mergers throughout the universe, the physics being universal even if the specific details vary. The gas clouds in the galaxies do collide despite stars passing between each other without contact, molecular clouds from the Milky Way and Andromeda interpenetrating, the collisions being dramatic because gas behaves differently from stars, pressure and shock waves affecting gas dynamics, the ram pressure compressing molecular clouds, triggering gravitational collapse that leads to star formation, the collision zones becoming regions of intense starburst activity where thousands or millions of stars form in concentrated periods, timescales of millions rather than billions of years being fast by galactic standards. The bright blue massive stars appearing in regions of collision shine intensely but briefly, their luminosity being thousands or tens of thousands of times the Sun's, their lifetimes being only millions of years compared to the Sun's 10 billion year life expectancy. The massive stars evolving rapidly through their life cycles, becoming red supergiants, exploding as supernovae, the violent stellar evolution releasing enormous energy, creating expanding shells of hot gas, enriching the interstellar medium with newly synthesized heavy elements, iron and oxygen and carbon being distributed. The starburst phase being brief but intense, consuming available gas rapidly, exhausting fuel within perhaps a billion years, creating spectacular displays of stellar phenomena, massive stars and glowing nebulae and supernovae being common during the merger's active phase. Though again, whether observers exist billions of years hence to witness this spectacle remains uncertain and perhaps unlikely. The galaxies don't merge immediately on first passage, instead passing through each other and separating, their velocities reduced by the gravitational interaction, falling back toward each other for another encounter, the process repeating multiple close approaches over the next few billion years, each passage stripping more material, heating the stellar orbits, gradually destroying the disk structures, the spiral morphology being lost as orbits randomize, the end result after several billion years being a single large elliptical galaxy, spheroidal distribution of stars with little rotation, the spiral structure that defined both original galaxies being erased by the merger process. The supermassive black holes at the centers of both galaxies eventually merge. The black holes sinking toward the center of the merged system through dynamical friction, their gravitational interactions with stars gradually removing orbital energy, bringing the black holes closer together. The final merger happening rapidly once the black holes are within a few Schwarzschild radii of each other. Gravitational wave emission carrying away the remaining orbital energy, the black holes spiraling together and merging in a fraction of a second, creating gravitational waves that ripple across the universe, detectable by sufficiently sensitive instruments. The merged black hole, having mass around 9 million solar masses, the sum of the two original black holes minus a few percent, radiated as gravitational waves. Some have nicknamed the merger product Milkomeda, a portmanteau of Milky Way and Andromeda, the informal name being memorable, though not official, the merged galaxy being designated by whatever naming system exists billions of years in the future, assuming astronomical civilization continues, the nomenclature being the least of concerns in this far future scenario. The point being that two spiral galaxies become one elliptical galaxy, the transformation being irreversible on cosmic timescales, the memory of the original spirals being lost except in the phase space distribution of stars, forensic archaeology of stellar orbits potentially revealing the merger history, signatures of the collision persisting in orbital properties even after the morphology has settled. Star formation in the merged galaxy eventually declines as gas is consumed or heated or expelled by stellar feedback, the interstellar medium being depleted, new star formation requiring gas that increasingly isn't available, the galaxy becoming red and dead, containing old red stars but few young blue ones, the stellar population aging, the galaxy fading, the process taking billions of additional years but being inevitable, entropy always increasing, order always degrading, the available free energy being gradually exhausted, the merger product eventually becoming a slowly evolving relic, a monument to past glory, the stellar populations aging toward cooler temperatures and lower luminosities. But you will not witness this. Earth will not witness this. Humanity, if it still exists, will have migrated elsewhere or evolved into something unrecognizable or perhaps ceased to exist. The sun will have exhausted its hydrogen fuel, expanding into a red giant phase around 5 billion years from now, Earth's orbit being engulfed, or at least rendered uninhabitable, by the increased solar luminosity, the oceans boiling away, the atmosphere being stripped, the planet becoming a barren, scorched world, or being entirely consumed, life on Earth having perhaps 3 billion years remaining before the sun's evolution makes the planet uninhabitable, the galaxy merger happening after Earth is already gone, the abstract future being unobservable except through imagination and simulation. You drift through deeper time now, watching not just the future, but contemplating the past, the Milky Way's entire history playing out in your mind's eye, billions of years of evolution compressed into contemplation, the perspective being cosmic rather than human, measuring time in billions of years rather than seconds or years. The scales being appropriate for galactic evolution, the tempo being slow by human standards, but appropriate for the processes being described. The Milky Way formed approximately 13.6 billion years ago, only 200 million years after the Big Bang that initiated the universe, making our galaxy one of the older structures among the first generation of major galaxies, though exact formation timeline remains debated. Different components forming at different times, the halo and bulge being oldest, the disk being younger, the current morphology being the product of billions of years of evolution and multiple minor mergers. The first stars formed from metal-free primordial gas, pure hydrogen and helium with trace lithium from Big Bang nucleosynthesis. These population 3 stars being massive and short-lived, rapidly enriching the interstellar medium with heavy elements through supernova explosions, none surviving to the present, all having burned through their fuel and exploded or collapsed billions of years ago, but their chemical legacy remaining, enabling subsequent generations of stars to form with the heavy elements necessary for rocky planets, and ultimately for life. The halo formed early through accretion of smaller protogalactic fragments, dozens or hundreds of small systems merging together, their stars now comprising the stellar halo, the old metal-poor stars with highly elliptical orbits reflecting their origin in disrupted satellites. The globular clusters also forming early, surviving as bound systems, while the diffuse stellar component mixed and phase-wrapped, the archaeology of formation being readable in the oldest stars' properties, chemical compositions and kinematics preserving information about the early galaxy. The disk formed later, gas cooling and settling into a rotating plane, conservation of angular momentum creating a disk geometry, stars forming from this disk gas, the thin disk containing most of the stars visible in the Milky Way, including the Sun, which formed approximately 4.6 billion years ago, relatively recently in galactic history. The Sun being a third-generation star, containing heavy elements from previous stellar generations, the oxygen in the air we breathe, the carbon in our bodies, the iron in our blood, all forged in stellar interiors and distributed by supernovae, stardust literally comprising living organisms. The spiral structure emerged through density wave theory, gravitational instabilities in the disk creating spiral density waves, regions of enhanced density that rotate more slowly than stars' orbit, stars passing through spiral arms, being compressed and sometimes triggered into star formation, the spiral pattern persisting, even though individual stars don't remain in the arms, the pattern being a wave phenomenon rather than material structure, analogous to sound waves propagating through air, the wave being persistent while particles move through it. Star formation continues in the present era at a rate of approximately 1 to 2 solar masses per year. New stars forming in molecular clouds in spiral arms, the process ongoing, the galaxy remaining active, blue stars and red giants, and planetary nebulae and supernovae marking recent star formation. The full range of stellar evolutionary stages being visible, the galaxy being a living system, dynamically evolving, not a static structure but a changing one. The future extends vastly beyond the Andromeda merger, trillions of years into the future, when current timescales become inadequate, when the unit of time becomes billions of years rather than years or seconds, when the universe itself has evolved beyond recognition, expansion having carried distant galaxies beyond any possible observation, the cosmic microwave background having redshifted into invisibility. the night sky going dark, except for local group remnants. Star formation will gradually cease as gas is exhausted or heated too much to collapse, the last stars forming perhaps hundreds of billions of years from now, after which no new stars appear, existing stars aging and dying, the galaxy becoming progressively dimmer, red dwarfs being the last survivors, their long lifetimes allowing them to persist for trillions of years after sun-like stars have expired. But eventually even red dwarfs exhaust their fuel, becoming white dwarfs, or perhaps directly collapsing to neutron stars or black holes, depending on initial mass. The far future becomes increasingly cold and dark, stellar remnants cooling, white dwarfs fading to black dwarfs, neutron stars cooling, black holes slowly evaporating through Hawking radiation, even this process taking incredible timescales, a solar mass black hole requiring 10 to the power of 67 years to evaporate, numbers so large they're almost meaningless. The heat death of the galaxy occurring on timescales, making the current age of the universe seem like an eye blink. The ultimate fate being maximal entropy, thermal equilibrium, nothing remaining but cold, dark, inert remnants drifting through expanding space, the long, slow fade into silence and darkness, the galaxy's entire luminous history being a brief, bright phase in an eternity of darkness. But this is abstract future, so distant as to be almost fantasy, the present being what matters, the current epoch being when the galaxy is alive, stars forming and dying, planets orbiting, potentially life existing on some of them, the possibility that you yourself, reading or listening to this, are one brief moment of consciousness arising from stellar matter, briefly aware before returning to the cosmic cycles. Consider humanity's place in this vast structure. Earth's location is approximately 26,000 light-years from the galactic centre, about halfway out along the galactic radius in the Orion spur between major spiral arms, neither in the crowded dangerous inner regions, where supernovae and stellar collisions are more common, nor in the sparse outer regions, where heavy elements are scarce and planet formation may be inhibited, our location being perhaps in the galactic habitable zone, regions where conditions favour planets and potentially life, though whether such a zone truly exists remains debated, the concept being speculative. The timescales are humbling. Light from the galactic centre takes 26,000 years to reach us. We observe Sagittarius A star as it was when Neanderthals still existed, shared the world with Homo sapiens, the delay being substantial even by historical standards, by astronomical standards being brief, photons travelling at the ultimate speed limit, no information travelling faster. One orbit around the galaxy takes approximately 230 million years, a galactic year, last time the Sun was at its current position relative to the galactic centre, the dinosaurs had recently appeared, the Triassic period giving way to the Jurassic, the entire span of dinosaur dominance fitting into one galactic orbit. Human history being a tiny fraction of one orbit, all of human civilization occupying perhaps 0.00004 of one galactic rotation, a moment, a brief flicker. The scales make our existence brief and local, all of human history happening in one tiny spot in one minor arm of one ordinary galaxy among hundreds of billions, the perspective being humbling, the realization of insignificance being unavoidable. Yet we've figured this out. Brief local beings have understood the vast structure containing them. Consciousness arising from stellar matter has comprehended the system from which it arose. The achievement being remarkable, despite the humbling perspective, perhaps the universe becoming aware of itself through observers arising within it. Remember those ancient Greeks seeing a mysterious Milky Band, wondering what it could be. Remember Galileo resolving it into stars, the first step toward comprehension. Remember Herschel patiently counting stars to map its shape. Remember Hubble proving our galaxy is one among billions? Remember radio astronomers mapping hydrogen throughout the disk? Remember Gaia measuring 1 billion stars precisely? The journey of understanding spans millennia, each generation building on the previous, the progressive enlightenment requiring patience and persistence and countless individuals contributing their efforts, the long, slow arc of human knowledge bending toward understanding. It is late now. You stand under a dark sky far from city lights, perhaps in a desert or mountain location, a place where the natural darkness of night remains, where the Milky Way is visible in its full glory rather than hidden by light pollution. The experience being increasingly rare as artificial illumination spreads, but still accessible to those who seek it, the journey to darkness being worth the effort. You lie on your back on a blanket or directly on the earth, the ground beneath you solid and stable, your body relaxing after the effort of hiking to this remote location, eyes adjusting to darkness over the course of 20 or 30 minutes, pupils dilating, rhodopsin building up in your retinas, sensitivity increasing, more and more stars appearing as your eyes adapt, the process being the same as it was for ancient observers. The physiology unchanged across millennia. The Milky Way stretches overhead from horizon to horizon, a river of faint light made of countless stars, individually too faint and distant to see separately, but collectively creating a pale glow, the band being wider in some directions and narrower in others, the irregularity reflecting dust lanes and spiral arm structure, the detailed geography of the galactic disk being visible to patient eyes, not requiring instruments, just darkness and time and attention. The brightest region is towards Sagittarius, the direction of the galactic centre, the combined light of billions of stars in the central bulge creating enhanced brightness. Though the actual centre is hidden behind dust clouds, the obscuring lanes visible as dark rifts splitting the Milky Way, the Coal Sack and Great Rift being prominent dark regions where dust blocks background starlight, the silhouettes of molecular clouds being visible as absences, dark nebulae defined by what they hide rather than what they emit. The Cygnus region of the northern Milky Way is also bright, the view down the local spiral arm showing rich star fields. The complexity of structure being apparent, the Milky Way not being uniform but having texture, regions of brightness and darkness, the view being three-dimensional even though projected onto the sky's two-dimensional surface. The distances varying enormously, nearby stars, bright, distant stars faint, dust clouds creating the dark lanes, nebulae glowing in certain regions, the layered structure creating the complex appearance. The fainter outer regions toward Auriga and Perseus show the opposite side of the galaxy, the view looking outward through the disk toward the anticentre. Fewer stars in this direction because we're looking toward the edge of the disk rather than through its densest parts. The asymmetry revealing our off-centre position, the evidence being visible to naked eyes without needing instruments, the basic geometry being apparent through patient observation. The realization settles over you like the darkness itself, slow and gentle. The understanding that you're looking into the disk of your home galaxy from inside it, that the pale glow is billions of stars, that their light has travelled for hundreds or thousands of years to reach your eyes, that the photons now triggering chemical reactions in your retinas departed those distant stars when human history was different, when generations have lived and died in the time light has travelled. You are made of atoms forged in those stars, stellar nucleosynthesis, creating elements heavier than hydrogen and helium, supernovae distributing those elements, molecular clouds condensing to form new stars and planets. elements assembling into molecules, molecules into cells, cells into organisms, organisms into conscious beings, briefly aware of the cosmos that created them. Stardust contemplating stardust, matter becoming conscious and comprehending its origins, the circle being closed, the cosmos observing itself through you. The listener is drifting now, the story fading gently into sleep, the vastness of the galaxy becoming a backdrop for rest, the billions of years and trillions of stars becoming abstract rather than concrete, the cosmic perspective being comforting rather than overwhelming, the sense of being part of something larger being reassuring, the knowledge that the galaxy continues regardless of individual awareness, allowing relaxation into sleep, trusting the larger patterns to persist. The Milky Way turns slowly, completing one rotation every 230 million years, the stars orbiting the centre at various speeds, depending on their distances, the spiral pattern rotating, material flowing through the arms, stars being born and dying, the cycle continuing, the rhythm being ancient and patient, unaffected by human concerns, the galactic machinery operating on timescales, making individual lives brief, but the patterns eternal, or at least persisting for billions of years, which amounts to eternity from human perspective. From ancient myths of spilled milk to precise measurements of billions of stars, from thinking we're at the centre to knowing we're in a minor arm of an ordinary spiral, from seeing a mysterious band to understanding galactic structure. The journey spans millennia, the understanding hard-won through centuries of observation and thought, the accumulated knowledge being humanity's collective achievement. The gift passed down through generations, each adding something, building toward comprehensive understanding. The Milky Way stretches overhead tonight, as it has for billions of years before humans existed and will for billions more after we're gone. Its light reaching your eyes now having travelled across space at the ultimate speed limit, some photons coming from nearby stars only decades old in travel time, others from distant spiral arms having travelled for thousands of years, the light being ancient, the view into the past, seeing the galaxy as it was not as it is, the information being delayed by the finite speed of light, but the delay being small compared to galactic timescales, the image being current enough for understanding. The galaxy turns, stars orbit, gas clouds collapse, new stars form, old stars die, the cycle continues, the pattern persists, the rhythm ancient and patient, the timescales vast, the process ongoing whether observed or not, consciousness being optional, the galaxy existing and evolving regardless of observers. But you exist now in this moment, briefly aware, connected to the cosmos through the photons entering your eyes, the atoms comprising your body, the thoughts arising from neural activity, all of it being natural processes, physics and chemistry and biology, the cosmic evolution producing structures of increasing complexity, eventually producing beings capable of understanding the system that created them. Rest now. The story is told, the journey through time and space is complete, from ancient hillsides to modern satellites, from mystery to understanding, from one observer to billions of stars mapped, the Milky Way remaining mysterious in some ways, dark matter and black holes and formation details still being studied, but the basic structure understood, our cosmic address known, our place in the larger universe specified, the framework established within which future discoveries will fill in details, the patient work continuing, the cycle of observation and understanding persisting, but for now, rest. The galaxy continues its rotation, the universe expands, the dance goes on, and you, briefly aware of it all, can rest knowing that the patterns persist, the cosmos continues. The great slow machinery of galactic evolution proceeding regardless of individual awareness, providing comfort in continuity, peace in persistence, rest in knowing that you're part of something vast and ancient and ongoing, stardust briefly conscious, contemplating the cosmic context, understanding the home galaxy, knowing where you are in the vast structure of the universe, then resting, sleeping, dreaming perhaps of spirals and stars and the long, slow turning of the galaxy through billions of years of cosmic time.